Hello and welcome everybody to today's lecture in the course of Protection in Electrical Power Systems about failure modes and fault analysis. So, let's start concerning the failure modes and fault analysis with the failure modes. Failure modes are classified, as we can see here, in 5 categories, of which the first 4 are the most important ones when it comes to fault analysis at present. So let's start with a 3-phase short circuit, which is a close on earth or final stage of a developing fault. So first let's see some deplorable pictures. What happens? Let's see this building to our left side. The building has experienced a short circuit of some 20 kiloamps and the arc pressure has made the walls to explode and to fall down. Also the switchgear inside this substation is severely damaged. This happens if there's a short circuit of 20 amps for more than 10 seconds. By the way, this was a protection failure where neither the protection nor the backup stage tripped, so it burned and finally the fault was cleared. In contrast to this, we have the single phase to ground faults, which experience usually much less fault current than the 3-phase short circuits do. So let's see some pictures. So to our left side we see the picture of an arc that burns in a 110 kV substation, and the story is that it has burned for approximately 10 minutes already until it was photographed, and this was with a current of approximately 100 amps. As you can remember, or as you know, if you insert something special into the zero sequence path of the short circuit current, then the fault current is reduced. That has happened in this case. Also to our right side we see a fault in an overhead line system where a conductor has broken, fallen down to ground, and if you look carefully into the middle of this red circle you see a white blot. This is where the arc burns, and again this arc is assumed to burn with approximately 100 amps, and that has already gone on for quite a long time. So, the fault analysis helps the engineer to understand ex post what has happened, and I will show you how this is done systematically. First, let's start with the short circuit, the 3-phase short circuit, which is the most severe one in an electrical power system. So we start systematically first with the appearance of this fault, the 3-phase fault. Then we see that the voltage triangle collapses symmetrically and the traces repeat this. So let's concentrate on the first set of traces, which is the 3 phase-to-phase voltages. As we can see, these 3 phase-to-phase voltages collapse uniformly for all 3 phases. The same happens to the second set of voltages, that is the phase-to-ground voltage. So these voltages also collapse uniformly, and the third trace, which is the neutral displacement voltage, does not collapse at all because zero sequence is not involved in such a fault. The next type of fault is the phase-to-phase fault without involvement of ground. So this is a very rare fault, by the way. Maybe it is caused by swinging overhead lines. Again, we start with the same systematic. We start with the appearance of the fault, then with a triangle. And here we see that the triangle collapses only in 2 phases. The 2 phases in this case are L1 and L2, and the traces repeat the same pattern. For example, take again the first set of traces, which is the phase-to-phase voltages. In these phase-to-phase voltages, one phase-to-phase voltage collapses, whereas the others remain more or less unchanged. The next set of traces are the phase-to-ground voltages. Here we can see that 2 of these phase-to-ground voltages are afflicted, and this is important in this kind of failure. There is no neutral displacement voltage because, as can be shown, zero sequence current and zero sequence voltages are not involved. The next one, in contrast to the first phase-to-phase voltage collapse, is the phase-to-phase to ground fault. This is mostly the second stage of a developing fault which started with a single phase to ground fault. Again, we start with the appearance of the fault, and now we can see that the 2 phase voltage collapse versus ground. And this pattern is repeated in the traces. So again, we start with the first set of traces, which is the phase-to-phase voltages. Here we see that one phase-to-phase voltage collapses. And when it comes to the phase-to-ground voltages, we can see that two phases collapse versus ground. And amazingly enough, the third voltage goes up. So this is very characteristic for this type of fault where ground is involved. The reason is when we look into the voltage triangle that before the fault, the line to ground voltage in L1 was L1 to neutral, and now this has risen up by 50%. And here for the first time we have the appearance of neutral point displacement voltage, which means ground is involved, we have zero sequence current flowing, and from this zero sequence voltages develop. The last type of voltage which I want to analyze with you is the line to ground fault, also commonly known as ground fault or earth fault. In this case, one phase is connected to ground. So this is, by the way, the most common insulation fault or the first stage of a developing fault. Again, we start with the appearance of the fault, and now we can see that the whole triangle has not changed so much. That means the phase-to-phase voltage remain unchanged, but the whole triangle has moved away from neutral, in the sense that L1 has become the neutral and the two other phase-to-ground voltages have risen by a factor of √3. Here we can see this in the traces. First, the phase-to-phase voltages are uniform, they do not change, and this is the reason why operation of the loads is not severely afflicted by such a fault. But when it comes to the second set of voltages, the phase-to-ground voltage, we see that one voltage collapses and two voltages rise. And another indication for involvement of ground, we have a very substantial neutral point displacement voltage. So this was today's chapter about failure modes and fault analysis. And I thank you very much.